the actual value, so that could be for us what we would call your experimental value. So what did you actually get in class, what did you actually get in lab, and then your percent error calculation. So go ahead and include that on what to memorize as well. So that's your actual value minus your theoretical, all over your theoretical. Arguably, it depends, and I don't know necessarily, but a lot of exams, assessments, textbooks, teachers like to put in the absolute value to make that always positive. I think there's value in the negative sign. Whatever you get as a number, make it either positive or negative so you get the right answer there, right? Okay. A few other things that came to mind as we're going through there. Well, I showed you this when we were doing atomic structure and we were actually introducing Schrodinger's equation. What we said was this, we said consider light, it's like an electron, or electron is like light, wave-particle duality. Showed you the equations, we didn't calculate them with it. However, going back through some of the Science Olympiad stuff, I saw several questions that dealt with these calculations. So at the simplest form, right, this is Planck's constant. That would end up being on the review, that ACS would give you that. That's not something arguably you should know, hopefully. No, I think it is, if we look at a review sheet, right? This periodic table. Yep, they give you Planck's constant, so you should be good there. F is frequency of light, E is energy. So these might be equations that you commit to memory as well. Speed of light is 3.00 times 10 to the 8th meters per second in a vacuum. So memorize the speed of light, 3 to the 8th. And this Greek letter lambda is wavelength. Okay, let me give you a second. Okay. Would you agree that the higher the energy, the greater the frequency, or vice versa? The greater the frequency, the greater the energy. Is that true? Yeah, they're directly proportional. So high frequencies have high energies, large energies, and the relationship between frequency and wavelength, if you move one of these variables to the other side, it shows up on the denominator, so I'll just write that like this. Frequency is inversely proportional to wavelength. As wavelength grows, the frequency decreases, and vice versa, right? So this relationship is directly proportional. How that looks is if you have, let's say, an energy level like this. So you have some protons, neutrons, and electrons in here. Let's just go ahead and call this the first energy level, n equals 1. So dealing with those quantum numbers, n equals 2, n equals 3. Atomic absorption, moving from one energy level, being bombarded with some energy. This energy can be calculated as E equals HF. Promotes that electron to a higher energy state. It's very short-lived, and then that electron will decay, right, back down to a lower energy level, giving off some amount of energy in the process. Okay. So think about this carefully. If an electron moves from n equals 1 to n equals 3, that required a huge amount of energy. What color of visible light does that correspond to? So if n goes from 1 to 3, it took a large amount of energy to do that. What color of light might that be? So I'm asking about RGB.
Does it not give off light because it's taking in energy?
Sorry? Say it again.
It's taking in energy, so it's not giving off light.
Yeah, but what color of light might have promoted that excitement? So which one's big energy, which one's little energy? High energy, low energy? This is high energy, right? This is large frequencies. So high energies, large frequencies, these are tiny wavelengths. And then the vice versa is true on this side. So as you go this direction, these are all true. Okay, so here's a question that's shown up on the Science Olympiad sort of questions at some point over the course of history, is if an electron is going to decay, this is atomic absorption, atomic emission, decays back down to a lower energy state. Which one of these gives off the largest wavelength? If n goes from n3, let's say, to n equals 1, n equals 4 to n equals 2, n equals 4 to n equals 1, or let's say n equals 1 to n equals 4. Okay. Which one of these transitions, 1 to 4, 3 to 1, 4 to 2, 4 to 1, will give off the largest wavelength? Okay. Remember, largest wavelength corresponds to smallest frequency. Very, very low frequencies. Low frequencies correspond to what energies? Low energies. So which one is the lowest energy? Which one? Sorry.
4 to 1.
That's got a lot of energy, right? That's a big gap, right? You give off a lot of E. Keep going. Okay, we could do that. How, if we're just going to say what's the difference, it's 2, right? What's the difference? It's 2. So these two give off the same amount of energy, fair? And if they give off the same amount of energy, that 2 is less than this amount of energy that it gives off. Let's just quantify that as 3. So one of these two, very low amounts of energy given off. Low energies correspond to low frequencies. Low frequencies correspond to big wavelengths. You see how that progression kind of rolls there? So arguably maybe the thing would be like, go ahead and put a 5 here so we have one option. And definitely this would be the largest wavelength, the lowest amount of energy. Which one gives off the smallest wavelength? So in essence, which one would give off violet light?
4 to 2.
This is high energy.
4 to
4 to 1 gives off 3. 4 to 2 gives off 2.
Oh, it's 5. 5 to 3.
Yeah, this one, right? Because this value, E, is very large. If you have a very large E, you have a very high F. If this is very big, what's this?
Small.
Very small. And then you could go, oh, here we go, small wavelengths. Okay, so be able to rationalize something a little bit like that. And then if you're given two numbers, if something's asked to, I don't know, if they give you something like a joule is a unit here, or they could also give it to you in terms of electron volts. If they give you a number, you know what the unit of energy is. You know what the unit is, joules, right? Planck's constant, that's a given to you. Can you calculate frequency? Yeah, right? Just plug it into this equation. You have two variables, calculate F. Same thing with the speed of light, constant. Can you calculate F? If they say this is 498 nanometers, what should you do to this unit here?
Make it meters.
You should make it meters, right? Or convert this to nanometers. So the problem's answer will be in some sort of hertz, which means these units have to be able to cancel. All right, so just keep track of a few things like that. I sold out on several questions. Okay, let's try to crash cram here a few things and see if we can just jog the memory a little bit. So stop me if you have questions. Otherwise, this will be pretty extensive here. Maybe not the best way, but let's try to pick up on some of those free points, if you will, as we go through there. All right, so I'm just going to work off this sheet kind of from the top down, working our way through.
Top down in what section?
Or what assignment?
The molecular structure and bonding?
No, sorry, this honors chem 1 review.
Yeah.
Outline
It's the like
topics.
4-page
Yeah.
packet.
I don't have that.
I got
You only had it-
extras up here.
He only handed it to a couple people once, but to be honest with you.
I think I gave it to you last week, yeah?
No,
Did I not?
no.
Oh.
It's fine.
No, you did not.
It's fine, it's fine.
Wait,
Let's
this
just keep
thingy?
going.
It doesn't matter, just keep going. Let's
No,
You're
it's
in
gonna go
this
print more.
thingy?
Yeah.
Oh, well, I got
Yeah.
it. It's just right there, but that's it.
Okay. Let's go ahead and do this.
It doesn't matter, just keep going.
Okay, in terms of significant figures, right? Accuracy, precision, etc. Do negative signs affect the number of significant figures you have? No. Does it matter if it's in the exponent? No. Does 10 to the fifth matter at all? No. If you're doing pure significant figures, leave it in scientific notation. Do not take it out of there. This has no effect, nor does this have any effect. Anything that's not a zero is significant. Any zero between two, yeah, Gloria, there's one if you want. You got an extra?
No.
Oh.
We only have one between the three of us.
Yeah, I'll print one more out.
Okay.
Any zero that comes between two non-zeros is significant, right? This zero is between two non-zeros. And then what about zeros that fall to the right of the furthest right value if it's not a zero? So the zeros to the right of the furthest right non-zero value are significant if
There's a decimal.
there's a decimal. Where? Anywhere. Literally anywhere in the number, right? So all of those are significant. Let's reverse that. Okay. Any non-zero number is significant. Any zero between two non-zeros. Any zero to the right of the furthest right non-zero number and a value that contains a decimal is significant. These zeros are not significant ever.
Because they're to the left.
Any zero that comes to the left of the furthest left non-zero number is never significant. So in these two cases, this would be a kind of a free 2 points if you remember sig fig rules. Let's go ahead and convert this into scientific notation.
3.04050.
Okay, let's just go 3 sig figs. This is going to be negative because we need to move this decimal to the left. If it looks like it's between the 3 and the 0, 1, 2, 3, right? Being able to convert it back to this equation. Plus or minus, so this is accuracy and precision. The value associated, or the uncertainty associated with this by default should be choose the furthest right significant figure, put a 1 underneath it, zeros everywhere else, carry down the decimal. This is the uncertainty associated with that value. Right? Does this going to, is this number or this uncertainty showing you the same thing as writing the uncertainty as an entire number? Yes. These two things are the same. So if it's in scientific notation, do not change it. If it's out of scientific notation, you're asked to find the uncertainty. Don't put it into scientific notation. Just do one or the other. But if you have this, choose the furthest right significant figure, zeros everywhere else, right? Go ahead and carry down the decimal. This is your uncertainty here. Okay, let's move that up there. Accuracy, precision, uncertainty. Percent error, we did that. Percent yield, scientific notation, SI base units, length, mass, time, temperature, amount. Properties, density, okay, density. Density is,
Quick question on
Yeah.
sig figs. Is it always the last significant figure? So is it, let's say instead of it being 304050, it was a 1 at the end. Would you still do plus or minus?
yeah, like if this was a 6, yeah, still same, still 1.
Okay.
Yeah, always a 1. Yep.
On the ACS exam,
Yeah.
for like, turning it into scientific notation, will they tell us how many places?
Yes.
Or if they don't, do you just want us to put the full?
No, they would tell you. Yeah, so they'd say round this to 3 significant figures or 5 significant figures or something like that. Density, mass by volume, go ahead and memorize that one if you include that onto your memorization sheet if it's not there already. The units typically associated with that are grams per milliliter. 1 milliliter is equal to 1 cubic centimeter. Nice little conversion to have. Get yourself a graduate cylinder, put some water in there. How do you read the graduate cylinder? Where do you read it at?
The bottom of the meniscus.
Yeah, the meniscus. I've seen that on a question before at some point as well, that shows up. Read the meniscus there at the bottom. If this value, let's say, is 50, and this is 51, take a guess. Oh, I guess I have to put some marks in here.
Probably 50 and a half.
Okay, pretend there's 10 there. But we at least know it's 50, fair? We at least know it's 0.1234. If you're close enough, it's 0.4. And then do we guess one more position here? What do you think? I mean, for sure we know it's 50, and for sure we know it's at least 0.4.
Oh, then yeah.
Then yes, you have to guess one more. You get to choose what that point is, but the question would be, what's the accurate measurement here? Is it 50? Is it 50.4? Is it 50.455? Is it 50 point, is that all our options? Those are all our options. So which one of these is correct measurement? You would choose this, you know for sure those, and you take one guess. One guess, right? Always, on every single measurement, let's say. Okay, take an irregular shaped object. It'd be very difficult to calculate the volume of that object to be able to use on the denominator here. Place it into it. The meniscus will go up because the volume of water is displaced. How do we know what the mass of this object is? You weigh it. So let's just say it's a 10-gram object. And if this now is, let's say, 55, and this is 54, with the marks in there again, give me a reasonable value of what that might be. Oh, sorry, let's go up here. Give me a reasonable value. Just take a guess here.
54.9.
Okay, 54.9. 0. Okay, so there's our guess again. What's the volume of this object?
4.5.
Okay, but in general, right? You're saying this is where you started, this is where you end. So the 54.9 minus the 50.45 is the difference of the water change as soon as you dropped in the irregular shaped object, right? So that 4 point whatever would go here, right, on the bottom. And that would be your density of that object, okay? All right, let's keep rolling. Just throwing a whole bunch at you. Decicentimilli,
Micro, nano, pico, 1.1333.
decahectakilo. Decahectakilo. Okay, so metric prefixes in terms of base unit down. Decicentillion, micron, pico, going up, decahectakilo, mega gigatera. Save yourself some time. Chapter 4, when you get this handout, if you don't have it already, it's going to say the scientists on them. You do not need to know the extensive notes that we took over those scientists. What you're arguing is this: with the cathode ray experiment, there was a stream of subatomic particles that were deflected, right? And they came out to be negatively charged. Okay, walk away from the cathode ray. Then Robert Millikan, negative particles suspended in air, showed their mass and their charge. Okay, walk away. Rutherford, what he proved? Rutherford. So Thomson had the electron, cathode ray. Millikan said this is the mass and charge. Rutherford said sciencey things like the only other subatomic particles on
Protons.
Protons, yeah. So it's shooting an atom, in essence helium, through a gold sheet. So you have the gold foil experiment, and they're deflected at large angles to find the proton, which is in the nucleus. That would be, I think, personally sufficient for your scientist model. Bohr's model of the atom, as you're looking through there. Your temperature conversions, you will have to memorize those. I doubt they give you those. Have I seen that question? Don't remember. Not, but I would just go ahead and.
1.8 Celsius.
You know what my wife asked me this weekend?
Or
She was looking.
9/5 if you prefer a fraction versus the.
True story. We're driving. She's like, we need to get the kids sleeping bag for the summer because we're going to try camp. She was looking it up. Had the rating in Celsius. Took that opportunity to teach her how to convert to Fahrenheit. Bam. There it is.
Glad you're
It was cool in the moment. It was cool in real life application. All right, so these two. All right, keep moving on. Well, yeah. On the periodic table, remember carbon has a 6 and it has a 1200. Don't say top, don't say bottom. Whatever's the whole number, that's the atomic number. The atomic number tells you the number of and electrons. Every single element on the periodic table, as written, is electrically neutral. This is the molar mass of that. You guys have been using this a lot, so just don't forget that's grams per mole. That is calculated by knowing the average weighted mass of all naturally occurring isotopes. So how do you calculate that? That's legitimately, you take the percent abundance of one isotope times its mass, plus the percent abundance of a second isotope times its mass, and so on and so forth, plus dot, dot, dot. So if you're given 3 isotopes, and this one is 40% abundant, this one is 40% abundant, and this one's the remaining 20% abundant, right? You have the mass, whatever that would be, I don't know. Carbon is 12, carbon 13, carbon 14, right? if you take percentages, be careful here, I don't know that they would do this in the answer, but if you take 40 times 12 and 40 times 13 and 20, then you have to divide the whole thing by 100 to get out of a percent. Otherwise, just go ahead and put 0.4, do the same thing, hey, and do 0.2 on that one as well. Thank you, appreciate it. Thanks. Sure. Okay, so that's how you calculate the average weight of mass. What is the most abundant element of carbon in the universe? As far, or on Earth, on Earth, on Earth. Which one? Most abundant isotope of carbon on Earth.
12?
12. Why?
I don't know.
You're right. Because the mass on the periodic table is the closest to the value of 12. What's the most abundant isotope of nitrogen? 14, right? So those, if you round up or round down, tells you the most abundant isotope. What is an isotope?
Charged element.
Neutrons.
Okay, so how many protons do these have? Carbon, these are the isotope mass numbers, 13, 12, 14.
Protons is also.
They have 6 positive, right? How many electrons if they're electrically neutral? Right? How many neutrons for this one?
7.
How'd you get it?
You subtract.
Well, what'd you subtract in words?
Protons from the.
Yeah, so you took the mass number minus the atomic number because the mass number tells you the number of protons plus the number of neutrons. So you get this from the atomic number. We go from there. So we have 6 neutrons here and here. 8 neutrons. Okay. I'd definitely probably be prepared for one of those. They like their isotopes. I think it's stupid.
You think it's stupid?
I do.
Go, Morgan.
I do. I think it is. Alright, keep moving on. Chapter 5, wave particle duality of light. Heisenberg's uncertainty principle. What is it? Heisenberg's uncertainty principle.
That you will never know the location.
And?
Momentum.
There you go, which means you do not know which way the electron is going, how fast it's going, and its exact position simultaneously. The more certain you are about one of them, the less certain you are about the other components of that, right? Quantum mechanical model of the atom, Schrodinger's wave equation, energy levels, etc., SPDF orbital notations. Okay, I'll point, you say. I'll point, you say. Alright, which block is this? SPDF?
S.
This one.
P.
X, Y, Z, P, X, P, Y, P, Z. What are the D's?
Oh gosh.
Yep.
I don't even remember. X, Y.
Yep, keep going.
That's what I know.
Keep going.
Y, V,
Yep.
X, V, Z squared.
Yep, there you go.
But D
X
squared minus
squared
Y
minus
squared.
What am I doing? Just listening and not writing. D, X, Y, D, X, Z,
It's like
D,
D X
Y,
squared,
and Z.
you know?
Not even close to being right. D, Z squared, D, X squared minus Y squared, right? S, do you have to know?
No,
Okay.
but kind of.
What is copper's electron shorthand notation? Copper.
What, argon 4 to 3,
No, 9.
9. 9. Right, a 9. Thank you.
Which one is correct?
Yikes.
That.
Okay,
It's
yeah, that one.
Which one?
technically.
Why?
Because it
Because
fills
you
all of
want
the
to fill the
orbitals.
final.
Filled or half filled. So either half filled or completely filled is more stable than partially filled. Completely filled, not even. It's impartially. Impartially filled?
It's
Yeah,
close.
you get what I mean. Not completely filled, not half filled. Completely filled and perfectly half filled, way more stable. So what would silver's be?
Silver?
Yeah.
The same thing, but 5s2.
What's chromium?
Chromium.
What's chromium's? Chromium?
Argon. 4. No. Oh.
Argon? Go ahead. 4s1, 3d. So when do you start seeing these exceptions? In the D block, when you're either in the 3d4 or you're in the 3d9, because you only need one more electron to move there, right? Okay, keep going. Give me the series of quantum numbers. Right. Remember those things? Yeah.
Not
N,
enough.
L, ml,
Oh god.
yeah, and ms,
We have to know this?
yeah.
Oh, no.
Well,
Okay.
N is just the level.
So,
Like that.
Alright,
so
so-
It's just the energy.
1, 2,
Alright, how do you find, like, to your point?
Energy level.
So what does that mean though on the periodic
So
table?
S, wait, there's
The-
no 0?
you know, one,
Oh,
two,
shit.
on the side, the other,
There you go.
know? I
The
couldn't-
row
I
you
didn't
are
know how to
in,
describe
the
that.
row you are in is the energy level for the S and the P block, the main group
It was
elements.
a processing. of
L, how do you find it? 0 to, you go from
Is it
0 to
3?
n minus 1.
Oh.
Yep, that's
Oh,
your
I just
range.
know it, I guess.
ML is negative L all the way to positive L, and MS is either negative 1/2 or positive 1/2. Those are your options. In the first energy level, this word L corresponds to the shape. This corresponds to the energy, principal energy level. So this is a principal quantum number. This would correspond to what we call the sublevel in terms of the language. What's this correspond to? Energy, shape. Energy, shape. Energy, shape. You can look, you can be as big, you can be a certain shape, or you can be a different arrangement. So orientation. And this is what? Spin. Okay, do electrons actually spin like that? No, it's more a mathematical principle than it is a physical reality. Okay. Every time you go down in energy level, you gain a new shape. So this is 0, this is 0, 1, this is 0, 1, 2, and this is 0, 1, 2, 3. Oops. What does 0 mean? That's S. What does L mean, or 1 mean? Right, and you have 3 orientations, and you have just the S. I'll just write just like that. So you have S, SP, SP, D. So if a question wants to know what the, and I will do this in a second, actually, oh wait, I will do this in a second, PX, PY, PZ, all these, DXY dot dot dot, PZ squared, so there's 5 of them, right? All the ones we just listed out. And then what's 3? That's your F. So S, P, D, and F notation, okay? We said you can put 6 electrons in the P's. Each orbital holds 2 electrons, 2, 4, 6. What's Hund's rule?
To fill
The lowest first. No, that's not.
or is it one?
Off bow is you have to fill the lower
Yeah.
energy ones. You can't do this. You have to fill the lower energy first.
They have to have opposite spin.
Hund's,
Question, is that
You
how?
have to fill
I don't know
Huns.
which
half
one.
before you can fill it full.
yeah, there you go. Hund's, you have to be half filled.
Okay.
Or not, or 1 electron in each orbital of degeneracy. That means each orbital that has equivalent energy. And notice I'll always come back to this axis. Same spin, 1 each one before you can go back and put a second one in to there. Right? That's Hund's. What's Pauli's exclusions principle? You have off bow, Hund, and Pauli.
They have to have the opposite
There you
spin.
go. You can't have up. That violates Pauli's principle. So no 2 electrons can have the same set of quantum numbers. They have to differ in some way. And here, do these 2 electrons that I've circled, do they have the same energy? Do they have the same energy? Yeah. So let's go ahead and write out the quantum numbers. That's n equals 2. What's L for those 2 electrons? Electron 1, electron 2, what's L? L is the shape. What's the shape of those 2 electron densities? I heard it, just be confident. 1, yeah. Why, how'd you get that though? It's P, right? So they're both in the second, they're in the P. What's their orientation? Okay, so you can make that anything you want to, but let's choose something reasonable. If we choose PX, then the values of ML would range from -1, 0, 1. What would be here? -1, 0, or sorry, -2, -1, 0, 1, 2, right? The actual quantum numbers. So PX, PY, PZ. So we can make this -1, 0, 1. Okay. Those so far, Pauli says that's okay still, except for the last quantum number. what's the quantum number for these two electrons for MS? There you go, positive 1/2, negative 1/2, okay? Follows exclusion principle, nice. Alright, let's keep going. Sorry guys, I know, it was horrible on a Monday to do this. It'd be even worse tomorrow to try and do it.
Yeah.
I think that takes care of all the electron configuration stuff, right?
I think so.
Periodic table,
Okay.
periodic trends right quick, and then we'll do molecular bonding. What electronegativity increases, so the desire for an electron increases as you go up and increases as you go over. You're going over should make sense. Non-metals want electrons, metals don't. That makes sense, right? You want electrons. Going up means you're getting smaller as an atom, so the effective nuclear charge, another periodic trend, is the desire for those valence electrons to be pulled in based on how much positive charge I have. Remember I said this is the first energy level, second, the third. It's harder to hold on to the third than it is the first. So Z effective increases as you go to the right and increases as you go down. It's not as drastic down as it is to the right, but it is there. So the desire for, or how strongly those electrons are attracted. Ionization energy, which way does it increase?
To the right
Ionization.
and up.
Increases to the right. It gets harder to remove an electron because fluorine really wants it. And it gets very easy to remove an electron from a metal, right? Lithium wants to give it up. What about here? Going top to bottom or bottom to top? So is it easy for francium to give it up or lithium? Francium, because it's bigger, it's further away, rip that electron off. So ionization energy increases the energy needed to remove an electron as you go up and to the right. Electron affinity, the energy released upon the addition of an electron. I really want an electron, but now if you give me an electron, it becomes stable. Who has high electroaffinity values? To the top right again. Yep, that's it. Electron affinity. Fluorine really wants it, very stable. What about here? Yeah, it doesn't want it at all, right? So give off a ton of energy. Electron affinity increases as you go to the right and increases as you go up. So ionization energy, electron affinity, and electronegativity all follow the exact same direction, up and to the right, for sure. I did mention on your handout, if you don't know what to do, apply a periodic trend, right? And that can get you moving in the right direction for sure. Okay, molecular bonding then. Let's do a few examples. Remember sigma, pi, that sort of thing?
Unfortunately.
Yeah, I remember those. Boron, carbon, nitrogen are all irregular when you do molecular orbitals. Oxygen, fluorine, neon are the same. Hofbrinkel, hydrogen, oxygen, fluorine, right? What does that mean? You do. Those are your diatomics. Okay, so let's look at this for a moment. Let's just make up some random compound here. Sort of random, I guess. Okay, not completely random. We need it to kind of work out-ish. Alright, this is the Lewis-Dot structure. We don't need to worry about naming this one in particular. Okay, well, let's identify each type of bond and hybridization that may or may not be occurring in there. So let's start with hybridization first. sp, sp2, sp3. What do those mean?
How many were those?
When you see something, and when you see a certain shape, geometry, you should say these. What shape geometry does this correspond to? Linear. Next one. Trigonal planar. And tetrahedral. Alright. Carbon. What molecular or electron pair geometries do you see? Carbon. This one. Okay, so that's sp3. Can hydrogen hybridize? No. Because it only has one electron in the s. It's not going to shuttle it to the p and get rid of it in the s, right? Here, this one. sp3. Here. sp2. 1, 2, 3 different regions of electron density. This one. Be careful, there are lone pairs there. sp3, that's still tetrahedral, 4 regions of electron density. Every time you take an atomic orbital and you hybridize it with another atomic orbital, how many hybridized orbitals have you formed? So the number of atomic orbitals equals the number of hybridized orbitals. 2 atomic orbitals, you make 2 hybridized. How many hybridized here? 3? And here? 4. So let's check. We use a different color. Carbon has an sp3 here, 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 and here. And those are binding to hydrogen's 1s non-hybridized atomic orbital. Fair? Not hybridized. This carbon, this one, and this one. This sp3 of carbon is interacting with this sp3 of carbon to create a covalent bond, a sharing of electron density. Okay. This carbon, you have 1. Be careful with this one. There's 2, and there's 3, and I've intentionally left out that other one. What is that bond in pink? Because I can only, for sp2, I can only make 3 hybridized bonds. What's the pink one?
Unhybridized.
It's unhybridized. And because it's a double bond, it's pi. Okay, so in terms of sigma versus pi, anytime you have a single bond, that's sigma, right? Is this a single bond here? Yeah? So those are all sigma bonds, right? Maybe I shouldn't put them in the same color. Sorry. Let's do pi and blue. Do I have any other pi bonds? No, everything else is sigma. What does sigma mean? Bonding occurs along the internuclear axis connecting. So let's say you have this bond and you're looking at this one. They overlap along that axis. That's sigma. What does pi mean?
I'm on the other axis.
If that's Z, you have some density here and here, right? And there's somehow some overlapping character between them. Every pi bond is an unhybridized p orbital. Okay. What else? For that one, help me out. Formal charge. Give me the formal charge of oxygen. 6 valence minus 2 bonds, 1, 2, minus 1, 2, 3, 4 electrons in a lone pair. 0. What are we trying to do with formal charge?
Get the least amount of charge.
Yeah, you want as many zeros as possible. And if something has to be a negative, who gets the negative? The one that's more electronegative or less electronegative? More electronegative. So go for as many zeros as possible. If you have to have a charge, make that charge as close to 0 as possible. If there has to be a negative charge, put on the most electronegative atom. Yeah.
For the electron part, does it have to be in a lone pair?
For this number here? Yeah.
So let's say there's only 3. Would you?
Yeah. Then that
Yeah.
number would be 3.
Okay, yeah.
Yeah.
So it doesn't have to have a. Okay, yeah. It's hard.
Yeah, I got it. That is also mean those stop structures. Give me the geometries of these right quick. Molecular geometry. Give me an example. Something that has 4 bonds. Carbon,
CH4.
H4, right? Methane. Now watch, if I take one of those atoms off, but this is a lone pair, what's the molecular geometry? Trigonal pyramidal, because those bend, right? What's the bond angle here? Between any of the atoms, if that's on there? 109.5. What about here? Bond angles, because these decrease. 107.5. And if we drop one more off, 104.5. So in general, it's like a 2-ish degree change, right? That's water, so H2O. What's molecular or electron pair geometry? 1, 2, 3, 4. Tetrahedral. And the shape, molecular?
No.
Bent. Yeah, bent because of lone pairs. What about this one? I have 1, 2, 3, 4, 5 regions. Electron pair geometry. Trigonal bipyramidal. Molecular geometry is the same. If we take, let's say, 1 off of this axial position, what shape? Let me do like this. Is that easier? Yeah. Seesaw. Okay, go back to our structure. I take one again off of that axial position,
T.
there's our T shape. And if I take a third one off,
Then
linear. There. Okay. This one, I have, here's one face, two faces, 3, 4, and twice. That's octa, 8 hedral faces, octahedral. What's the bond angle here? 90 as well. So everything's 90, right? We don't do this, so we just go here and then here. If I take one off of here, okay, you see the square? And it comes up to a point, square pyramidal. What about this one? That's square planar, right? Square planar. All right, those are your basic molecular geometry shapes. Anything else was there, Scott? I'm forgetting. I don't know that.
I mean, it's my favorite stack. It's everything. Alright, now.
Resonance. How do you know you have resonance or not?
Because the one and single ones.
Keep going.
And they can.
And they have all
they
of the
can-
same atom or element bonded to it. Jesus. I
Yeah,
can't
that's the second part.
speak.
So the requirement is Y has to be the same atom as Y. Has to be the same atom as Y. If this was X, would you have resonance?
No.
No. So you have to be the same atom and you have to have a double or a triple bond. Fair? Can you have 1 and 1/4 bond character? Sorry, there's a gnat. What, is that an actual thing?
Yes.
1 and 1/4 bond character? Can you have bond character that's half? How do you find it? So bond order, bond character, is found by taking 1/2 the number of bonding minus anti-bonding. What happens if you get a 0 here?
And they don't, it doesn't exist.
It doesn't exist. That bond is not existing to any significant extent. What happens if, as this number gets larger, what is it saying about the relative stability of those interactions? Sorry? It's getting more stable because you have more bond character. It's releasing a
More
lot more
polar.
energy. Which one's harder to break? A triple bond or double bond?
Triple
Triple.
Which one's shorter?
One.
Triple's shorter.
Short.
The single bond very long. Literally think of it as dancing with somebody, right? No, I'm
I've
serious.
had this conversation.
Right? If you hold one hand like this, you can spin, you can distance yourself from the person, and you can come back. If you're double bond, you can't do it, right? And even more, if you lock a leg, now you really can't twist at all. So you just decrease that distance between you. So very rigid, fixed, short, non-existent, long, flexible, able to bend and flex more freely on those. All right, polyatomic ions, you do have to memorize several of those, but let's do the 8. So I'm on the nomenclature part now of everything. So this is like,
Wait,
yeah,
what polyatomic ions do we need to remember?
yeah,
We'll
let's
go
do
right in a
these.
second.
Let's do that right now.
Okay.
Let's do your abnormal ones. What's this one? Ammonium, hydronium, acetate, and hydroxide. You can't get those by looking directly off the periodic table. Oh, okay, there's a trend, right? Right. But everything else, if you are a non-metal, so the turquoise blue or sky blue up there, right? Boron, the transition metal line over. You're not a noble gas. We said boron, carbon, nitrogen. Forget oxygen, and then everything else. So I'll just kind of go like this then. No, sorry. What am I doing? There. Okay, just go with it, right? And this will be fluorine. Okay. Boron, carbon, and nitrogen are their proximity to oxygen. Everything else is the proximity to a noble gas in terms of its charge. Okay, but let's start here. To figure out the 8 form of a word, this row and this column are how many oxygens? 3. So bore, let's do nitrate, NO3, right? And let's do bromate, BRO3. Now to get the charges, nitrogen is 1 position away from an oxygen, and bromine is 1 position away from a noble gas. So there's the charge. If I want the ite form, what do I do to NO3?
Take away the electron.
Do I keep the charge? Keep the charge?
Yes.
What's bromide?
You said bromide, and I was like,
Bromide,
what do you mean?
yeah. What's one less oxygen, two less oxygens?
It's,
Hypoite.
Hyponitrite, right? And then the hypobromite. And which one do we have left?
Perchlorate. I don't know.
Perchlorate.
I was just trying to say
I actually just wrote perchlorate.
I said hypochlorite.
Actually, that's not a bad strategy. Memorize one and then you got it for the rest. So this would be NO,
What?
NO
Oh, I said
4
per.
-1, NBR.
4.
Again, we're just practicing, doesn't mean they actually exist or stable.
I don't know.
So those are your polyatomic ions. So I'm going to argue, don't memorize this. Well, don't memorize all the polyatomic ions possible. Memorize the 8-ite, hypoite for one scenario, like the chlorate, legitimately. Do perchlorate, chlorate, the ite, and the hypochlorite, and say apply that same pattern to everything else. Commit these to memory. There's a few other little ones that you've used, like cyanide. Occasionally, if you see MnO4, take your best guess, but it's like permanganate, manganate. Okay, a couple of those things that show up periodically. But otherwise, don't plot your extensive polyatomic sheet, like Miss Lefevre's, and try to memorize all that. That's just not going to go well. Okay. All right, let's take a little break. Give you a decision break. You want to go outside for a second?
Yeah, I won't bite my eye. I
One
know,
out.
just let the tears fall.
It's 48 hours from now. We gotta go.
Not even 48 hours.
Oh my
It's
god!
even
Mr.
46.
Morgan's panicking. I think we need to panic.
Okay, maybe I should have brought out
Where's
the
John? Where's John Wynn? We need to. Where's Calvin?
Calvin doesn't care, let's be honest.
Is that today?
Yeah.
Okay, tell them we didn't do anything. Make them feel better.
I mean,
Lie to
in
them.
a way, we really did.
Lie to them?
Oh
We didn't do anything new.
Okay, don't lie to them. Alright, let's keep going. We can do it.
It would make a difference. They wouldn't be able to come back to
We
it.
can do it. We can do it. Metal or non-metal? Ionic or covalent? Metal, non-metal.
Ionic.
Ionic. So covalent, two non-metals bonding together. What does Vespers say? The valence shell electron pair repulsion theory. Maximize distance to increase stability by lowering potential energy. Lower potential energy, maximize stability. Alright, nomenclature. Let's name a few other little things.
Oh god.
Remember how I said acids and bases are not officially part of your curriculum, but they always show up as an acid and base reacting together, even though you don't have to know all the things about acid and bases. Here it is.
Because I forgot.
Sure, you can share this with John Wynn
I
and
didn't
Mia
know organic.
as well. Alright, acid and base react to form salt, which is a metal with a non-metal, and question mark, water. Does it have to form water? No. But does it often? Yes.
Yeah.
Acid-base neutralization reaction. How do you know the difference between, or naming these acids? Binary acids, 1, 2 elemental symbols, different. Not binary, 1, 2, 3 different elemental symbols. This one has hydro something ic, so go ahead and say it, hydrochloric acid. So phase states here typically are aqueous. And this one, this is just chloric acid. So in terms of naming, the 8 goes to ic, the ite goes to
Is.
us.
Us is close enough.
So what's
There's no I in that.
Is,
go ahead and name this one. HClO2, chorus, and then HCl, hypochlorous, right? And then what about the other one? Let's do bases. We have very common things that are with hydroxides, magnesiums, sodiums, calciums, etc. They could be carbonates. So let me pull out the big picture items. Hydroxides and carbonates are generally speaking some of the most common bases. Also throwing into there, a lot of times ammonia can act as a base as well. Okay, now big picture, what do acids and bases do? The acid gives up the proton, it's a proton donor, and the base accepts the proton. Okay, so let's diagram that out here. Chlorine wants the electrons more, so it's slightly negative. This is slightly positive. if this hydroxide is in solution, so if that's soluble, then there's hydroxide floating around, fair? When that hydroxide gets close to, I'll put the negative charge on it, close to this hydrogen atom, it forces these electrons to move towards the chlorine. Therefore, this gives up hydrogen, yes? Because hydrogen is going to leave and go to the hydroxide. And then when it does so, we form water. And who accepted the hydrogen? Don't overthink that. This gave hydrogen up. Who accepted it? Yeah, this. Didn't this accept the hydrogen? So this is a proton acceptor. And this is the proton donor. And by donor, we literally mean hydrogen ion. So protons are just hydrogen ions. Okay, so at minimum, please, at minimum, just be able to do the naming and being able to predict what the products of those are. Okay, would that be okay? At minimum. What else would we form here besides water? We need a salt, which is a metal and non-metal. What's left over?
Sodium chloride.
Yeah, this happens to be table salt in this one. Alright, I'm going to go ahead and skip balancing chemical equations. I think you guys have done a lot of that. So balancing subscripts first, then coefficients, right? So balance charges, then balance the mass. Balancing in acid and base, let's, I guess, shove that to the side and just cross our fingers and say, let's hope there's not a 5-minute long problem. But, so don't spend hours studying that. If you have to take a hit on that, you know what I mean, for the redox portion of it. But simplified redox reactions would be F2 plus NaCl. Who's oxidized, who's reduced?
F2 is gonna be
This is 0, anything by itself.
reduced.
Okay. Fluorine goes to fluoride from a 0 to -1. That's a reduction. So that's the oxidizing agent. And then chloride goes to chlorine. And that's oxidized, which is the reducing agent. Fair? So definitely being able to predict redox that way. Combustion requires oxygen and produces heat. If you have carbon in the reactants, what else is produced? Carbon dioxide. If you have hydrogen in the reactants, water, nitrogen in the reactants with combustion. Carbon dioxide, water, nitrogen dioxide, you have sulfur dioxide, right?
Question,
Yeah,
why is it that the oxidizing species is a reducing agent?
it's the thing, yeah, when we say agent, this is the thing that causes something else to be oxidized. So it's the agent of oxidation, causes something else. Okay. Single displacement, double displacement, I think you're pretty good on those as a class. Your solubility rules, they don't give you, so you'll need to memorize some common ones. All nitrates, always aqueous, soluble. Lead, mercury, barium, heavy metals, normally insoluble. Acetates, chlorates, soluble, normally soluble. Hydroxides, insoluble, right? Carbonates, normally insoluble. So filing away some of those normally things, take your best guess. It's not a bad idea, it really isn't, to do that. Alkali metals. Alkali.
Soluble.
Always, right? Always soluble. Okay. All right, let's do one problem with Stoich.
Stoic.
Stoich.
Stop. Stoic, that just sounds wrong. Lefebvre pointed out that it was wrong.
It is. I agree with her.
Then stop saying it.
I can't. It's a habit now.
You're gonna forget 1 year that it's wrong, and then everyone's just gonna think that's what it actually is.
Yeah, that's
Yeah,
actually.
you're
gonna
poor
think you're
Gen
dumb.
Chem in a couple years. Sorry, what?
But they're gonna think you don't know what you're talking about.
Yeah, that's fair.
All right. Do we form water? Yeah.
Sometimes you're to think that. Okay.
And what else do we form? Besides sodium sulfate.
Yeah.
Okay. We'll go ahead and balance that. That is aqueous. It's not with an alkali metal. Okay, sodium hydroxide sulfuric acid. This is an acid-base problem, and as such, they're going to word it, if they have it, as an acid-base problem. They'd say something like Ooh, a titration experiment required the presence of, let's say 10 mil.
Throw it away, yeah.
Oh,
Oh, that was close.
Morgan had that one for sure. 10 milliliters of 1.5 molar sulfuric acid. In a titration experiment, the temperature changed, temperature was neutralized, or we neutralized it, blah, 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 phenolphthalein indicator was added, and you're like, what the heck, I've never done any of that, that's all acid-base chemistry. The problem just wants you to do stoichiometry, it just wants you to figure out the limiting reactant side of things. So what volume of sodium hydroxide is required to completely neutralize all of the acid present? That's not limiting the reactant. We're not saying how much product is produced, but we are saying how much reactant is required. Do we have to have a mole bridge?
Yes.
Because,
You have to convert it from.
yeah, you have information about one thing and you want to find something about something totally different. Fair? Okay, so do we use this equation?
No, because that's a 1-to-1, right?
Yes. Yes, 1-to-1 mole
That's a
ratio.
dilution, or.
That's a dilution, and this is not a dilution, this
It's gonna
is
be
how much is
dilution.
required to react. So to Jason's point, only if it's a 1-to-1, but I would say avoid that altogether unless the problem specifically wants to know
Of the
if,
same
if
compound.
you made a lower concentration sulfuric acid solution, use the dilution equation. Alright, set this up. Where do we start? Not here, because we want to find that out. Of these two numbers, which one?
Oh, nine.
Because this
We are
is a
going to-
unit, that's a
You
ratio.
have to balance it, right?
Yep, we will need to do that.
You're at milliliters.
Definitely. So milliliters, liters, we can do liters to moles of the acid. Okay.
Liters.
Yeah.
That's the molar.
Moles of the H2SO4.
And then the molar mass to make, or you don't even need molar mass.
Moles of NaOH. Okay. Now what?
We need
So
more,
far, this is volume
And then you do backwards.
times molarity. Gives us moles, and this is the mole bridge. Do it backwards, I like that. There's a law of symmetry. If you don't know what to do it backwards. I like
And
that.
then molarity of the other compound. And then
Moles of NaOH
liters to
to liters,
whatever.
liters to milliliters.
We need to balance the equation.
We do, yep,
Yeah,
to get our actual
definitely,
numbers.
you need two of the sodium hydroxide.
So in general, where's this number come from?
Known.
Yeah, that's your known, 10.00. 1 liter is 1,000 milliliters. You notice those cancel out, so don't have to worry about that, right? Thousands cancel. Okay, good. The molarity of the sulfuric acid, please be very careful with this. 1.5 molar is 1.5 moles per 1 liter. It does need to be written as 1.5 moles, right? Per 1 liter. The mole bridge here, we'll go ahead and balance this. We need a 2 here, okay? Is that it? 2?
Oh, yeah, you're good.
That's 4 hydrogens.
Oh, yeah.
To produce 2 waters. Yeah, there we go.
Oh.
So we need 2 moles of sodium hydroxide for every 1 mole sulfuric acid. Notice there are 2 hydrogens that can come off, H and H plus. How much hydroxide is needed to neutralize this one? This one.
One.
1. Right? And this one?
One.
1. So if there's only 1 hydroxide per compound, formula unit, you need 2 of those to give us 2 hydroxides. Right? Okay. Molarity here, this is 0.5 moles per 1 liter. Run it through your calculator, come up with a number. Is this number going to be larger or smaller than this value? Yeah, significantly larger, right? How do you know that without doing any of the math? Keep going.
And I needed 2 of it.
So, what do you mean?
I need 2 more.
Yeah, there you go. Yeah, so 2 parts of that. We are already lower concentration and we need twice as much of this as we do this. At minimum, just to react in the simplest, if they're equivalent concentrations, we would need double the amount of volume. Less concentration, we need even more, right? So if that's a multiple choice question, you have A, B, C, D, and it asks you to do the math and you get stuck, and you're like, I don't know what to do, I don't know where to find the numbers, what do I think about? If you have, let's say, if the value is like 50 mils and 9 mils, 6 mils, and 2 mils, which one are you taking?
50.
Yeah, just because rationally you need more of it, right? A lesser concentration, double the amount. Okay. So that's called acid-base neutralization. That's the stoichiometry that goes with it. And then try this on for size 2. I jotted down another problem that jogged my memory as I was thinking about all this. What if you have 0.15, let's say, liters of something like, something that's aqueous, let's say potassium nitrate, and it's 0.5 molar solution, and you add that to, let's say, 0.2 liters of something that's aqueous, potassium sulfate. All alkali metals are soluble, and let's call this 1.5 molar. What is the concentration of potassium ion? So those brackets mean moles per liter. What is that? What's the actual tangible concentration of potassium ion in that solution? Okay. All right, do a thought experiment. Do I know?
We do the MV1, right?
Could, but it's not dilution. Not necessarily. We're adding a beaker with another beaker together, the same much potassium ion is there. If I left this out here, could you tell me how many moles of this is in the solution? Moles of potassium nitrate.
Yeah.
Could we do a mole bridge to figure out how many moles of potassium ion are there? Could you do that same strategy here?
Could you also do percent concentrated?
Well, yeah, a little more tedious, but at minimum, you can find moles of this. You can do a mole bridge to get moles of potassium. You could do moles of this, mole bridge. And then to find concentration, I have the moles. What's my total volume? Okay, let's do it. So we have 0.15 liters of KNO3. We have 0.5 moles of KNO3. Mole bridge, moles of KNO3, moles of K. Second one, 0.2 liters.
K2SO4 times 1.5 moles K2SO4 over 1 liter times mole K2SO4 and 1K.
Okay. So at minimum, volume times molarity gives us moles. Volume times molarity gives us moles. Do the mole bridge to get moles of potassium. Are you memorizing equation? No, you're saying I need moles and I can find moles. We got that. In terms of the ratio here, 1 mole of potassium for every 1 mole of potassium nitrate. What about here?
2 and 1.
There are 2 moles of potassium ion for every 1 mole of this, because that's subscript 2, right? Okay. Once you get these two values, add them together. So you get the total moles of K. That's fine. And then what do you do with that?
You put it over the total liters.
That's this here. And the total liters is 0.150 plus 0.200 liters. Okay? Again, in a multiple choice question. Multiple choice. Is the concentration of potassium ion in these solutions added together greater than the concentration of the highest concentration?
No.
Think about that carefully. If I say 1.5 molar potassium sulfate is the concentration of potassium ion in that solution alone greater than the concentration of 1.5?
Yes.
Okay, it is, because you have twice as much potassium as you do the compound. See that? Is the potassium ion in here greater than that? It's equivalent. And now the only problem with a little bit of that logic is when you add two solutions together, now you have more liquid, or liquids components could act as a dilution. But at minimum, it gives you a starting point of either there might be a little more, or there might be a little less there. All right, the rest of the stoichiometry, the maximizing the amount of product is determined by the limiting reactant, fair? So whoever's limiting reactant dictates the maximum amount of product. Keep going. You guys are flying through this.
You're applying to this.
You are flying,
You-
we are
you
not.
guys are
My
hauling.
brain is not
We have-
comprehending this right now.
Wait, which
You-
chapter are we at?
Well,
Yeah.
these chapters, I
This
don't know.
was technically chapter 11 and
Have you been
12.
recording this whole thing? Thank you.
Let's see. Oh, yeah. I think everything else. Let's see.
Can we
got
take a
civil
break?
space until- hang on. Oh, God. Yeah, that got tutorial.
We're almost done.
15 minutes.
Gas laws. Gas laws.
Okay, those
Can
were
we
like
take
the
a
easiest
break?
thing to
Gas
They
laws.
weren't hard.
We can't. We gotta do it. We gotta do it. Then I don't have to do it tomorrow.
Are
Tomorrow's
we
just
having
a-
to deal with this tomorrow?
No, tomorrow's a full work day, I promise. If I can get through gas laws today. Alright, go.
Hurry,
I know, I'm trying.
get there,
Ah!
go!
Ah!
Remember!
He does add, but then he like writes calmly.
That's how I remember it.
It's like,
That's alright.
Like
running.
R.08.06.
They give you R.
Liters times the
Oh,
atmosphere divided
yeah,
by
you
the
are.
moles times the K.
You are. Alright,
Oh,
Hidner.
well, it's in my calculator.
P is
Thanks to Trevor,
inversely
shout
proportional to V. P is directly proportional to T. That's what this equation is saying. N is V is directly proportional to N. P is directly proportional to N. V is directly proportional to T, right? Those are all
I'm
the,
not
you
going
have,
to remember those.
you, that's this, that's this, that's what this is saying. Just change this to a sigma and, or alpha, yeah, alpha sign, right? And that tells you what the relationship is. P is directly proportional, V is directly proportional, so on and so forth.
You have N on there and V on there twice. So, V. Never mind.
Yeah. Hidner, when do you use it?
Pinder, when you
When you have one
One gas,
ideal,
One-
you know,
one-
no changing conditions.
Yeah.
One gas, one set of conditions.
ideal
Now,
circumstances.
the danger of that is you might
Two.
have, in
I
the
feel like you
problem,
need
you
to
might have a
mention
lot
that,
of
you know?
words about carbon dioxide and oxygen in the atmospheric
Oh.
air, blah, 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 and you're like, oh, lots of gases, I should do the total. Well, the information given is just about oxygen, right? It doesn't matter how many
Yeah,
things you
that's
say
why.
if the information is about oxygen. P1 equals V1, or P1 V1 over N1 T1 equals
equals
P2
P2 B2
V2.
over N2 T2.
The exact same thing, but with two.
It's
If the problem gives you something at atmospheric condition, it takes up some amount of space, it changes the new atmospheric condition and wants to know what the new volume is, what do you do with N and T?
They're constant.
Why?
Because
Yeah, if it's not directly alluded to, you may make the assumption it's constant, it's unchanging, right? So in essence, that simplifies to this now.
people
Not a new equation, just a different expression of that. And then the total pressure is P1 plus P2 plus P2.
Just add them together.
Which
Just add them together.
I feel like you don't even need an equation for that. Just like think
So-
of it.
PB
It's like
over
what's the
RT
total
times
pressure?
the
Oh my god,
sum
wait,
of
maybe I'll
N.
add them together.
So remember, define pressure, move volume to the other side. So that's this.
Total
Do that
pressure.
3 times, add them together.
Partial pressure.
Right? Add them together. Okay, effusion. Remember that one?
God. There's a
Uh,
lot going on right now.
a gas particle passing through a hole. That's
You're wrong.
effusion. What's diffusion?
Oh god. Oh my god, I
You
literally
know,
wait, I
wait.
did. Wait, you've actually Wait, you better keep that when we erase too.
What's the What's the line?
Gone.
The not, he just
No, you should say dead. Guts.
Oh, that's an exclamation point. I was trying to figure out why you put a hole in there.
Yeah. I'm gonna leave it there. I'll let Sarah too.
You better.
Yeah. Diffusion. What's that?
Expansion of gas to fill it in.
Yeah, it's just particles of gas moving in random chaotic motions. Gas particles take up no volume compared to the volume they occupy. They expand to fill the volume. They're highly compressible, high energy. Their speeds are dictated by the temperature, right? The greater the temperature, the greater Morgan. Ah!
Morgan, you're
No.
talking
What
too
are you doing?
fast.
Don't erase the
No.
net. Don't erase
erase
the
the
net.
Hey, check this. Number of particles.
Oh my god.
What
Why are
the-
we doing this
No,
now?
no.
What?
And this is your
Think, Mr.
temperature.
Morgan.
Temperature.
Think, Morgan.
Molecular
Think.
speed.
Are you
He's gonna
teaching
do
us
that
something
stupid-
new?
He's
No, no,
gonna
no.
do this.
No, no.
Oh.
Do this.
Oh, I bet you. I
No.
bet you.
This is the graph to show you what you've already known, but file this away because then you don't have to
Oh,
remember all
really?
the rules.
Oh really? Oh what?
Whoa.
Oh he is. Whoa.
Whoa. Oh, that's,
Oh okay.
guys, it's just a big roller coaster.
Alright.
No, we've
Which
seen
one?
this before.
Which one? Think about this carefully. If temperature is directly proportional
I
to
was
kinetic
too.
energy, where kinetic
I was gonna do the
energy
potential energy
is
thing.
this equation, V is speed. The greater the speed, the greater the energy. The greater the energy, the greater the motion of the
Okay, I'm
system.
ready.
Temperature. Which one of these is hot? Which one is cold? Choose the extremes. Don't choose the middle. Let's
Hot
get
is
into
the
it.
faster speed.
This is high temperature,
Oh yeah. Let's get it.
and this is low temp.
Quick
So,
question.
in general, and by what degree or temperature difference, this is just greater. So what this says is the average number of particles in that sample
God.
that have a greater molecular speed is
low.
greater at higher temperatures. So just things move faster at higher temperatures, and there's more particles moving faster.